Thanks, Hugo. Thanks a lot for the invitation. It's a pleasure to be in Berkeley and telling you about this work, which appeared last summer with Douglas Stanford and Cynthia Yan. Douglas, you all know, and Cynthia is a grad student working with Douglas at Stanford. So this talk is about some computations in string theory or toy models of string theory that we did last year. But I should also point out these other papers that appeared around the same time by Dionysius Aninos and Beatrix Mühlmann and Bautista. They were motivated by different considerations of de Sitter space, in particular two-dimensional de Sitter space. So I encourage you to look at those papers as well. Okay, so the basic object we are going to study in this talk is the sphere partition function, but without any operator insertions. So usually when you study, let's say, string theory from Polchinski, the thing you compute is a 2-to-2 scattering amplitude. That's the first thing you might compute. So you have two tachyons going in, two tachyons going out. So that is a sphere we all learn in string theory with 4 punctures. And we are supposed to do some integral like d2z and with some integrand. So that gives us the scattering amplitude. I'm not going to write this out. This is not important, but the integral looks something like this. Okay. So this gives the scattering amplitude. But in this talk, we are not interested in scattering amplitudes. We are interested in something much more basic, which is just the sphere of string theory without any vertex operator insertion. So this is the world sheet of the string. I want you to think of this two-dimensional surface as the world sheet of the string. So how are you supposed to compute it? Well, it's just some path integral. There's some x fields. There's some metric fields in string theory. And then there's the volume of the gauge group, which you are supposed to divide by, and there's some integrand. It doesn't matter what it is for now, but the point is string theory is a theory of two-dimensional gravity, so we have some x fields that tell us how the string world sheet is embedded in target space, and then there's the world sheet metric. This is a two-dimensional metric. And usually we fix to conformal gauge, and the metric degrees of freedom almost all go away. But in the case of the sphere, you are left with this annoying non-compact group in the denominator. Okay, so I hope this fact is familiar to many of you, that the round metric on the sphere has a SL2C group of conformal transformations. And in particular, this group is non-compact. So this is a case where going to conformal gauge leaves a residual symmetry in the denominator. So this is the thing. Now, we know that the answer, because of the topology, is supposed to be proportional to G string to the -2. Because any world sheet comes weighted by G string to minus the Euler character of the thing. And if we know some counting, this is also proportional to the 1 over the Newton's constant. So this is good, because things like Gibbons-Hawking on-shell actions and entropies of black holes are proportional to 1 over G Newton. So you might hope that some empty thing like this that you compute in string theory might tell you about contributions to things like the black hole entropy and things like that. A simpler example is we have a string theory in ADS3 times S3 backgrounds. You know, the ADS3 string theory has a Newton's constant, 1 over G Newton, which we know is proportional to the central charge of the boundary CFT. So you can ask this question, how does the world sheet theory in ADS3 know about the central charge of the boundary theory? How do you compute it from that? And these questions are not obvious, so these are interesting questions from the point of view of space-time thermodynamics, and we would like to answer them. So in red, the expectation is that this string diagram with no insertion should give just the classical value of the on-shell action on the background in which the string is propagating. So that's why it's interesting to study this quantity. But as I already mentioned there, the puzzle is that one has to divide by this volume of this conformal Killing group, PSL2C, which is infinite, And there is also no sense in which you can regularize this value. Okay, let me just make that comment. And another comment is that in all of the cases where we expect the sphere partition function to be interesting, like in a black hole geometry or in ADS3, the target space is non-compact. It's big. So that means that this integral in the numerator here is also infinite, because the string could be placed anywhere in space-time, and that's part of the integral you have to do. So you have a situation where you have an infinity over infinity usually. And if your target space was compact, then this is actually 0, because then you have something finite divided by infinity. So the sphere partition function is not interesting for compact target spaces, but most interesting target spaces are non-compact. So that's another comment. And this is actually unlike the disk. Let me omit this comment for now. I can come back to it later if people are interested. So what seems reasonably clear is that the sphere diagram is 0 up to effects having to do with the non-compactness of the target space. And this is consistent with the fact that if you look at the space-time effective actions that, for example, are written down in Polchinski's book, they look something like d10x root g e to the minus 2 phi times r plus 4 grad phi square minus 1/12 h square. You can show very generally that this thing on shell is a boundary term. So the bulk term is 0, and all the non-zero-ness of it has to come from these boundary terms. So it becomes subtle, because somehow the string worldsheet, which is moving in this non-compact target space, has to know about the boundaries of a non-compact space-time. And usually we can't put cutoff on the x space, because x is a field on the worldsheet. So putting a cutoff on big X is like putting a cutoff on your field range, which is kind of, we don't usually do that.
Can you go up one slide?
Yeah.
No, not that far.
Yeah?
About you and Polchinski.
Oh, sorry, yeah. Okay, since you're interested, maybe I can say, so the same story applies for the disk, where instead of doing a sphere path integral, you're integrating over a disk. And then this thing is a PSL2R, not a PSL2C. And what Liu and Polchinski showed in a paper from the 1980s is that if you compute the volume of PSL2R, there's an infinite piece which has a nice subtraction. Like you can just subtract it out and get a finite value for that group volume. So that's some procedure you can do. You can question whether it's a principal thing to do or not. But they said that's, sorry?
Can you think of the spheres two disks glued together in any useful way and make use of these results?
Not that I know of, because the gauge groups are different. Like there's a PSL2R modded out and so on. So if you didn't have that modding out, if you just have, let's say, you're trying to compute just a scalar field, Laplacian on the sphere. The scalar field Laplacian on the sphere does have a decomposition into two disks. But that's also a little bit non-trivial. Like you have to put Dirichlet boundary conditions on one disk and Neumann on the other ones, and so on and so forth. But yeah. But the point of this comment is that the sphere is a little bit more finicky than the disk, because this is something I believe is true, that if you go to superstring theory, then this PSL2R gets promoted to this super version of PSL2R. Don't worry about what it is, but whatever it is, it has finite volume, because the infinity coming from the bosonic directions, that's infinite, and the fermion directions give a 0. So together, the thing has a finite volume. And you can use this to give, by this kind of a computation of the D-brane tension in 10-dimensional superstring theory. So it's some number times 1 over the string coupling, and you can compute that number just by computing that path integral over there. Usually in textbooks, people don't compute it this way. People compute it by some factorization of a long cylinder. Like if you look in Polchinski chapter 8, that's how he does it. Like you start with the cylinder and then you cut it into two disks. But the point is the disk at least has a direct calculation in these supersymmetric settings. Okay, and here I was just saying that when we have a non-compact space-time, even the Gibbons-Hawking-York procedure, you have to put a cutoff, you have to put the counter terms, and then take a limit to get things like the entropy correct. So here is what we do. We don't answer this question in any of these interesting backgrounds, ADS3, Schwarzschild black hole, none of that. It's a possibly irrelevant warm-up, but we did it anyway. So you compute the sphere partition function in what is called the non-critical string theory. A non-critical string theory doesn't have this x at all. There is no x. And the fields that go here are the fields of a minimal model. So I'll explain what that is, but that's the theory. So you take a worldsheet theory which has no x's but has this funny minimal model on it. The point is you can compute a finite value for the sphere and also check it against its dual. The dual is some matrix integral. The matrix integral, maybe people are familiar with it. It's very much like the matrix integral dual to JT gravity. It's actually simpler because it has a polynomial density of states rather than a sinh. So there's a duality between non-critical string theory and matrix integrals. You compute this sphere diagram in string theory, and you check it against the matrix, and it matches perfectly. Now, these minimal string theories have a parameter. It's called this p. So minimal models are labeled by two integers, p and p prime. They have to be relatively prime. But here we just take 2 comma p, minimal models, which have negative central charge. So the central charge of the minimal model is negative. So what happens in this limit, p goes to infinity, is that you have 3 fields on the worldsheet. There is the minimal model, there is the Louisville, and there's the usual BC ghost. That's always there because we have the gauge fix, the to conformal gauge. So this thing has a central charge which is going to negative infinity. This has a central charge which is going to plus infinity. And the BC ghost, of course, has a negative central charge, negative 26. I mean, of course, you have to take the limit in such a way that the total central charge is 0. But this is, so there are some concrete expressions for the central charge as functions of p. But at large values of p, this Liouville central charge in particular goes to plus infinity. And the reason we want to do that is because in this limit, you can evaluate that path integral over there by a saddle point approximation. So the coefficient in front of the Liouville Lagrangian gets a big coefficient. So you can use just a direct saddle point plus 1 loop approximation to compute that integral. You don't need to use any fancy DOZZ formulas, bootstrap, and so on, because for finite values of p, this theory is very strongly coupled, and we don't have a Lagrangian description of it. But point is, in the p goes to infinity limit, there is a simple semi-classical way to do the calculation, and everything is very, very clear. And notice that all we are after is a dumper. We already know how it has to scale. It has to scale with g string to the -2. So if we are not careful about various normalizations, we are just going to miss the answer, because we really want to match all factors of 2 and so on in this calculation. Otherwise, it's not meaningful to do this. Okay, so here is a paper that from 1982 that already had the basic idea of how to do this calculation. It was by Sasha Zamolodchikov. It's called On the Entropy of Random Surfaces, shortly after Polyakov's paper on this kind of setup. But we go a little further and compute the one-loop determinant, are very careful about order 1 factors. Okay, are there any questions about the motivation and what we are computing and what is happening? Okay. So here is the main idea. So the theory we have now, in particular, let me erase this. There's still a sphere. One of the integrals is the integral over a Liouville field phi. So Liouville field is called phi. There are some other stuff like the BC ghost and the minimal model. Let's not worry about that. And there is this volume of PSL2C in the denominator. what's going to happen is that when you try to find the saddle points for this Louisville Lagrangian, you find that there's not just one saddle point, but actually a 3-parameter family of saddle points. So there's an infinite number of saddle points in the numerator, all with the same action. And they are such that they are related to each other by action of precisely this conformal group. So that cancels. So essentially the fact that in non-critical string theory you have the Liouville field around gives you a non-compact family of saddle points related to each other by a PSL2C transformation. So you get an infinity in the numerator and exactly the same corresponding infinity in the denominator so that the ratio is finite. This thing in blue is like the main point, the main conceptual point, which was already there in that paper I showed on the previous slide by Zamological.
That's an emerging thing at P-coding.
Sorry?
Is that must be emergent thing at the P-coding emergent only at the P-coding
Sorry, in the numerator. Yeah, because the saddle point method is only valid at that time. Yeah, but we expect that, anyway, let me just say, we are only doing in the, So that's the point, that there are lots and lots of saddle points. You need to find them all, and you need to cancel those saddle points with this denominator here. But the point is, there are still some conventional subtleties that give some order 1 ambiguities in this number, which are related to, for example, the conformal anomaly and making various choices in the path integral measure. Like when we integrate over a scalar field, you have to put a metric on the space of fields. So there's some constants in there and so on and so forth. So all that stuff will cancel in this ratio. If you compute the ratio sphere over disk squared, all those ambiguities will cancel the choices that you make. And what you will have is just a real number that you can compare between the matrix and the string theory.
Sorry, can you repeat the last point again? What were the ambiguities? Why is that before you take the ratio, it was still defined?
Yeah, because this d phi is not just a one-dimensional integral. This is a functional integral with infinitely many things. And to define the measure, you have to introduce, for example, a metric on the space of fields, right? So that constant shows up in the answers. I will show you explicitly that if you look at the answer for the sphere or the disk individually, you will have all these constants around that are not physical, that don't have any meaning, but they cancel in this ratio. One of the things that, for example, cancels is that the sphere is proportional to g string to the -2, and the disk squared is g string to the -1 squared. So you see, you want this to cancel because even though you have a duality between the matrix integral and the gravity side, S0 has an additive ambiguity in the language of JT. So you can always add a constant to S0, like it's not fixed by anything. So you can't match that to a matrix prediction unless you fix something else. So basically, this ratio is being taken to cancel that ambiguity, the additive ambiguity in S0, which corresponds to like a multiplicative ambiguity in G string. Okay, so here we go. That's it. So now we are into the calculation. We are going to just do it. There are 3 components to the calculation. You identify the saddle points, and you also compute the one loop determinant. That's the approximation to which we are going to work. Saddle point plus one loop, and then you have to divide by the volume of that gauge group, that PSL2C there. So that's basically the plan of the talk. You can do it for the sphere. You can also do it for the disk. I will flash the formulas for the disk. I will not go through them because of time, and the idea is very similar, even though there are some technical details that are harder for the disk. Okay, so this I have already said, but let me emphasize it again, that there's a non-compact manifold of saddle points, and here it is. So it's G mod H. So if H is the symmetry group that preserves your saddle, G mod H is the space of Goldstone bosons that you get. In the case of the sphere, the big group is PSL2C, and the subset that is fixed by one of the saddle points, which I will show you, is just the SU2. PSU2 is SO3, so those are just the rigid rotations of the sphere. And for the disk, it's similar. It's PSL2R, so those are transformations of the disk, and then there's just a U1 that doesn't do anything to the saddle point. Okay. So what's being said here is that in the numerator, you have an integration over G mod H. In the denominator, you have G. The leftover factor is the volume of H, but H is compact. H is just SU2 or U1, so that has a finite volume.
So it doesn't sound too much on a semi-classical limit. In a semi-classical limit, you can see it explicitly, like
Yeah.
saddle point. But if you just assume that in a finite B, symmetry is broken, you have close to manifold.
Yeah.
Is that enough to create that finite? Of course, you can't show the first statement.
Well, yeah, I guess it's reasonable that the fact that we don't expect any phase transitions as a function of P, so that the result will continue to be finite, just that the actual number will not match. And then you have to rely on some bootstrap techniques to find the actual answer.
But it's finiteness.
Yeah, but I think one wouldn't doubt the finiteness just because there is no phase transition as a function. There's nothing special happening.
You're doing one of things that you're
Sorry?
You're doing one of things that you're topologically deviating from P.
Yeah. So anyway, I have said all these things. Let me not repeat them. Let's just go to the calculation. So it's not.
Sorry, can you just can I actually ask you to just go over the once more?
Which part?
The points that you just skipped over.
Well, here I think these points will become more clear when we actually do the calculation. So maybe we should do it then, because I've said them in words and saying more words is not going to help. So here is how Louisville theory works. This ds hat square is just some fixed metric. Let's say it's just this sphere metric here. It has Ricci scalar 2. And Louisville theory is a theory of this field sigma. So your actual metric is e to the 2 sigma times this guy. Okay? And the Louisville theory has a central charge, which is given by this, 1 plus 6, 1 over b plus b square. And you take large C, as I was saying here, by taking b small. So b is small, C is large, and p is also large. Here is the action. So since b is small, you see this large term in the action, right? The action has a large overall coefficient, which allows you to do a saddle point. The action for sigma just has a kinetic term. There's a coupling to the background Ricci scalar, and this thing is the so-called cosmological constant term. So for the sphere, you would not have the second line. This is a boundary term in case you happen to be working on the disk, but we're not going to talk about the disk, so there are these three terms here. Okay, and then there is some order 1 term in the action that you also have to keep because we are working to this order, but this is the action. Now we are going to look for saddle points of this equation, and we are going to look for saddle points such that sigma is constant. So this term is not going to be there. This just gives r hat. R hat is 2. That 2 will cancel against the 2 that comes from here. So you get 1 plus something e to the 2 sigma equals 0. So that's the saddle point equation. So this is what I just wrote, is 2 plus this thing. So you see mu is positive. So for this thing to have a solution, e to the 2 sigma has to be negative. So that means that the metric, which had a e to the 2 sigma in it, is a negative definite metric. So that's the saddle point. And
but what about the third line in the action?
Sorry?
The third line?
The third line is small. It doesn't have a 1 over b square in it. So the equations of motion, it's enough to just use the first line. Okay, so that's it. The point is this is a complex metric because the equation of motion for Liouville are basically r equals -2. A sphere doesn't have r equals -2 unless you put a minus signature metric on it. So anyway, this is it. This is some log, and then there are shifts by I pi. So there's actually not one solution, but these infinitely many solutions labeled by this n integer. You do the standard thing, you plug the thing back into the action, you get this phase factor. So this is this 1 over b squared is the large thing, and you have some, just a concrete expression in terms of this. Okay, so this fact has actually shown up before in a paper by Maldacena, Turiachi, and Yang, in which they were studying de Sitter JT gravity. And as part of that, they observed that a sphere with a minus signature metric can have r equals -2. So that's what I already said. So you have spherical topology, so you need something special in order to have a solution in the first place. Okay, so there is one more subtlety, which is which of these solutions do we have to sum over? Again, this issues of contours and so on, which saddles to include, have been discussed recently. But the answer here is to sum over half the values of n. So our saddles had this n integer from -infinity to infinity, and you're only supposed to sum from 0, 1, 2 up to so on. So what that does is the phase factor here, that was e to the I pi over b squared 1 plus 2n. Once you do the sum, it turns into this 1 over sine pi over b squared. So I haven't justified it yet, and the purpose of the next few slides is going to be to justify that, why only half the saddles have to be included. And the one loop determinants for all of these saddles are the same. So the one loop factor will just go outside the thing. Okay, so why did we only sum over half the saddles? So consider this toy integral. This integral is the zero mode of the Louisville field. So the zero mode means it has no position dependence. So think of this sigma as phi. So it's e to the background curvature times sigma minus e to the 2 sigma. This is the cosmological constant term. This is the background term. The point is a is negative. That's going to be important. Now, this integral is not convergent because when sigma goes to -infinity, this term turns off. It's just 0. It's just e to the -infinity. So this is e to the negative times negative. So it's e to the positive. So that's why this integral is not well defined, and you need to choose a proper contour. And the contour that is shown here is this is the correct thing to do. So for the zero mode, you should think of this as the zero mode of sigma, and this is the defining contour here. And the reason to pick this is that makes that above integrand convergent and well defined on this end. On this end, there was never a problem. And now you see these dotted lines are the steepest descent contours, and you can deform the defining contour onto the sum of 0, 1, 2, 3, and so on. So those are the contours that you have to add to get the answer.
And did you guys check that the steepest descent contours from each of those saddles intersects the original contour once?
Yeah, you can just see that here, right? You can just take this and wrap it. The point is this black line here is homotopic to a union of all of these, right? Just with coefficient 1. Is that clear? Yeah. Okay, so that's it for the sphere. So I told you what the semi-classical saddles are, which ones you should sum over, and why. Are there any questions about that? Okay. Well, I have maybe one comment. If you stare at this integral and you substitute e to the sigma as t, this is nothing but the gamma function integral. E to the sigma is t, so you get t to the a. And a is large and negative. So the procedure that I have just described is basically the procedure you would use to get the asymptotics of the gamma function, but for large negative values of the argument, not for large positive values. For large positive value, there's the standard Stirling approximation. For large negative values, you have to use this reflection formula. And the reflection formula has a 1 over sine in it, which is basically this sine here, the sine pi over b square that appears. So you can sort of make sense of it that way. But anyway, the process for the disk is the same. There are the equations of motion for the disk. Now sigma is no longer a constant. It depends on the latitude. So by the way, when I say disk, we worked with the hemisphere metric, so just the northern hemisphere of the sphere. So this is the equation of motion, this is the boundary condition, and here is some solution. Note that the sigma again has this imaginary part ambiguity and has not just a constant, but it depends on the latitude here. Anyway, but most of the points are the same. You can compute the on-shell action, you can sum over those values of n, get something. Okay. Now we come to the questions that you were asking. What happened? What are these constants that I was talking about? So all those come in when you try to compute the one loop determinant. So you take your field, sigma, you expand it as the classical value plus a fluctuation. And the idea is to do the integral over chi. So you first introduce a metric in field space. So there's this constant c times the inner product between a change in the field, chi. This inner product is just the standard integral over the sphere. So you take a field, you take two different deformations, f and g, phi plus epsilon f, phi plus epsilon g, and this is the inner product. So this is a metric on field space, and the path integral is the square root of g of this metric. So you see it will have lots of c's in it, c times c times c for every mode of the field.
Right, but isn't that those c fixed by the action? Because that will also appear in the quadratic form that appears in the action of the.
No, so that is independent. See, the action is something you define independently. This is.
But whatever the action, what I say is you would like, in order to compute the one loop determinant, to write I equal to the inner product on that BS squared with the c that you just defined of the field times the quadratic form times the field, right? Whatever c that you choose will also.
No, it doesn't have to come in there. Because the action, I can just write it without any c's in it, right? There is no need for me to introduce a.
Right, then I shouldn't have said that the action will have a c, it's just the quadratic form that appears in your determinant will have a c.
Well, I'm not sure why those two have to be correlated.
Because of the way that the Gaussian formula appears, right? You have a.
No. There is just an action, which is e to the minus. Let's say for the case of just some field, like I can just put an arbitrary constant here, right? Minus x dot square plus grad x squared over 2. So this capital K, this is just an expression that has nothing to do with the metric that I try to put on the field space, because that thing comes in trying to define this guy.
Right. And when you compute that, the whole point is that path interval will be the determinant of some quadratic form, right? And the choice of that quadratic form does not only depend on the action, but what you meant by the measure.
No, you can be very precise about this. The c's just come here. When you do the Gaussian integral here, you just get factors of 1 over square root of k from the various Gaussian integrals. The c and the k are not related, because it's just very explicit, right? I mean, here you will expand x as some xlm, ylm, and you will write the action in terms of xlms.
Right.
And the metric here would just contain a c for each ln m, and then this integral will give you a 1 over square root of k for each ln m. So they are not related.
Okay.
Yeah. Usually that capital C drops out. That there's a theorem that if you have a normal path integrals, that capital C, you don't get it. But point is, in principle, it's independent, and you'll see that it'll cancel out in physically meaningful quantities. Okay, so here's what we do. We take our sphere saddle for sigma, put sigma equals, yeah.
Usually cancel off, is that right?
Sorry?
Is it correct that you usually cancel off?
Yeah. That capital C, well, it has to do with some this zeta function identities. So sometimes sum of some zeta functions can be equal to 0. In particular, that one has to do the fact that usually that capital C cancels, has to do with the fact that zeta of 0 is minus half. I can explain that more, but
in general quantum field theory, you just change the normalization.
sorry?
If you just change the normalization of quantum field, it's just
So it will depend on k. The answer to the integral will depend on k. This is like the mass related to the mass of the field. But it does not depend on the capital C. I mean, one can be very explicit about this and just compute the integrals and check. Yeah. I mean, for example, the easiest thing to check is a particle on a ring. If you have a particle, quantum particle that's just moving on a ring, so that's just this action, and this thing would then be the mass of the particle. You can just compute the whole thing with the capital C, and you will find the correct partition function, which only depends on the little m and not on the capital C. I mean, that is why thermal partition functions, for example, come out well-defined when you do the path integral correctly. It should not depend on the capital C. It should depend on things like the mass of the particle and so on. I mean, otherwise, we'll be all over the place. Like computing z of beta for some system, we will not get the right answers with integer coefficients.
But usually you divide by vacuum, so it's just vacuum amplitude, so it doesn't matter anyway.
Yeah, but for example, in a thermal partition function, that's well-defined, right? The integers there are well-defined.
Doesn't matter, like you use your scattering or something, doesn't matter.
Yeah, that doesn't matter. But if we're trying to compute, really trying to see that z of beta is integer times Boltzmann factors.
And then it's still just.
Yeah. So here is the quadratic action in terms of chi. So this partial chi squared represents the Laplacian on the sphere, minus 2. So we have to do this integral. It's very easy. We know the Laplacian eigenvalues, LL plus 1, you get a minus 2. That's it. It's kind of funny that the mass term comes out with a minus sign, but that's what it is. So the degeneracy of each of these is 2L plus 1. So we have to deal separately with the L equal to 0 sector and the L equals 1 sector, but L equals 2 and higher, you can just do it. Okay, so what's going on with the L equals 0 guy? The L equals 0 guy has a negative eigenvalue. Note that L equals 0 means chi is a constant, right? It was sigma classical plus chi. And chi, if chi is a constant, it's just changing the 0 mode of sigma. And the 0 mode integral was the one I showed you on that slide with the contour. And if you remember, the steepest descent contour was going vertical through the saddle point. So since it's going vertical, even though you have a e to the plus 2, this integral is well defined. Because the steepest descent contour is vertical, so the answer is convergent. So you get some I times some stuff. So you see that the B is showing up and the C is showing up in this combination. The B was in the action and the C was in the measure. But you do get both of the things. Sorry, this should have been L equals 1. So we have 3 L equals 1 modes, and they are 0 modes. Their eigenvalue is 0. So they are the things that I was telling you give the infinity in the numerator. Because there is no Gaussian suppression for them. They are 0 modes. So it's like you have 3 modes, chi 1, 1, chi 1, 0, chi 1, minus 1, that are all just unsuppressed Gaussians. It's e to the 0 integral for them. So those are the 3 modes that are going to be related to the action of PSL2C. So for now, we don't integrate over them. We set them delta function. We deal with them later when we figure out the volume of the gauge group. Is that clear? Okay, and then for L bigger than or equal to 2, it's a story. We just do this zeta function product and compute the infinite product by taking a log, putting a suppression factor, taking epsilon to 0, give some divergent terms, give some constant. So usually what happens in these kinds of things is that once you put the suppression factor, you get a UV divergent piece and then a constant. some logs, 1 over epsilon squared, blah, blah, but then you get some constants. Anyway, so that's what we are computing. And you can play the same game with the hemisphere. I'm not going to go over it. Again, you expand to quadratic order, write the eigenvalue equation, impose the boundary conditions, find all the eigenvalues, and just compute the determinant. Again, there are 2 zero modes here, which are given by this with some particular values of L and M that I don't remember now. But they're just e to the I phi times tangent of theta over 2. Okay, so it's basically exactly the same, except that we have 2 zero modes.
And why do you think that, is there any physical motivation to setting the C from this computation equal to the C of the sphere computation?
The C for the disk and the C of the sphere? Yeah, that's very important that it should be the same because that's the field space, right? So the measure on the field space is so-called ultralocal. It doesn't depend on the shape of your manifold. Like the measure on the field is basically like some UV effect that it does, like, that's the reason why you have things like, you can glue and split manifolds in quantum field theory. If your measure was completely different for different manifolds, you would never be able to stitch manifolds in quantum field theory. So this property is called ultralocality of the measure. The fact that capital C only depends on a little neighborhood patch of your space, no matter what space you put it on. Was that clear? So there is this overall integral over the space that you have to do, whether it's a disk or a sphere, and that gives important factors of 2 and 1 and so on. But capital C itself should not depend on which manifold you're putting it on. I mean, otherwise the whole stitching and things are out of the window. Like you can't do anything. Yeah.
So when, for example, if you look at Lagrange-Long's geometry for equation theory, when we talk about ortholocality, you can either choose to do the bosonic. I know you're not doing the scattering amplitude, but you can do the bosonic scattering amplitudes either by using ultralocality. You get all those functional determinants, you find all those measures on field space, or you can choose to give H-fixable path interval. You have an integration over ghosts, and those give you the functional determinants, right?
Mm-hmm.
But ultralocality doesn't, if I remember correctly, this is one of the things I want to ask. I don't think it works for the superstring, but earlier in your presentation you said that you also had an analogous calculation for this before the superstring.
No, I think it works. Like even if you have fermion fields, you will have some measure on that field space. It will be of a slightly different nature because the thing is now Grassmann. But you still have some measure, and you have to pick. If you have different kinds of field, their C's don't have to be related. Like the C for the fermion doesn't have to be obviously related to the C for the boson. But there should be something analogous even for fermionic fields. Yeah. Okay, so this thing I already sort of said many times. There's a PSL2C thing that we need to cancel. There's an SU2 which is preserved. The quotient group are those 3 L equals 1 P-wave modes. So here's it more concretely. So we have chi1, chi2, chi3. These are the 3 chis I wrote here. The SL2C has 6 coordinates. We split them into 3 and 3. These are the SO3 coordinates that rotate the sphere. These are the broken ones. We split it up into these 3. This S1, S2, S3 integrated will give the volume of SU2, which is just finite because it's a compact group. And the same thing happens for the disk. Okay, I'll explain the factor of 2 to the 3 halves. There are people who are interested, but it's important because we are interested in getting all the factors right. So here's what all these vectors that are broken and so on. So let's write the metric of the sphere in these conformal coordinates. So there's a z and a z bar, and a 1 plus zz bar squared with a 4. So this has Ricci scalar equals to 2. So these are the 6 conformal killing vectors on the sphere. Let's look at the first one, iz and negative iz bar. What is this doing? It is just rotating the phase of z, right, because of the I and the minus I. And because it's just z and z bar, the metric just doesn't change. So this first vector field is a part of the SU2. It's not breaking the symmetry. Let's look at this number 4. It's Z and Z bar. This is like a real rescaling of Z. Z goes to 2Z, or Z bar goes to 2Z. So then clearly this metric changes, right? So it's broken. So this B1, B2, B3, you can check. They break the metric on the sphere that changes, and that this S1, S2, and S3 precisely generate the SO3 symmetries of 125. And the point is, on the hemisphere, you only have the first 3, because the last 3 don't preserve the equator. They move the equator around. So 4, 5, and 6 are just illegal on the hemisphere. Okay, so again, one of these measures again comes in. And here it's important because you see, we are going to take this PSL2C. Well, that's also a group that has a Haar measure on it. But Haar measures are never come with a natural normalization. I can just multiply it with 1,000 and it's still a Haar measure. So what do I mean by volume of SL2C? The point is that this SL2C and the SL2R for the disk are both coming from the ghost zero modes. So you need a metric on the space of the ghost fields. And that is the thing that ties the sphere to the disk. So that's the thing that ties the volume of SL2C to the volume of SL2R, is a metric on the space of the ghost zero modes. So the zero modes here that we're talking about, the C ghost, so that's the C. And this 3/8 pi has just been chosen for convenience. You could put it to like capital D or something. Doesn't matter. So this is the metric which determines the volume of PSL2C. And you see here, this factor is the same. That's the ultralocality. But you're integrating it over a different space, either the sphere or the hemisphere. And that difference that gives the factor of 2 to the 3/2. Okay, so now we are left to compute how, when we act with one of these geometrical transformations, the B's, the B1, B2, B3, how the sigma changes. And that's simple. Like, we have the whole metric, the full metric. That should be invariant. Well, that's the definition of how the Liouville field transforms under PSL2C. So if this part was not invariant, then sigma is not going to be invariant. So this is how it transforms. So the zeros are the ones under which the metric is symmetric. And the other 3, you see, these are proportional to the spherical harmonics with L equals 1. This is cosine theta, this is sine theta, and this is the third one. So you see that when you do these geometrical transformations, the sigma shifts by the L equals 1 spherical harmonics. Anyway, now you put everything together. This is just computing that factor, because the spherical harmonics have to be properly normalized and so on. And let me just show you the final, this is the answer. Action summed over saddle points, which give that 1 over sine. One loop factor, negative mode, zero mode, higher L modes. This is the gauge fixing factor. The same thing here. Okay, so you see there are all this C floating around everywhere, both here and here, which will cancel. That's non-trivial that it cancels out. Okay, but we are not done yet, because we just focused on the Liouville. I've been just hammering about the Liouville, but there's also the minimal model. So you need to compute the sphere over disk squared for the minimal model. The BC ghost is 1. Okay, you do that. You look it up in the yellow book, whatever, and then this is the answer. It's a very simple answer. Sphere over disk squared is just P times this alpha to the P plus 2. What is alpha? I didn't explain. Alpha is related to the boundary term in the disk. So the disk we are using, my title of the talk had FZZT in the title. FZZT boundary conditions have a boundary cosmological constant, and that alpha is related to that. So this 136 is the final answer. which one can try to reproduce from the matrix integral side, and one does. Okay, are there any questions? I'm obviously not going to go into the details of the matrix, but this is like a good time to just even finish the talk.
Why are you writing 1.000?
Because there are various constants along the way that we computed numerically. Like these, we were not analytically powerful enough to compute these zeta function products analytically, and we just gave up trying to look for them. So we just, well, the divergent parts, the 1 over epsilon squared and so on, are easy to find analytically. So you take numerically, you subtract it out, and you get it. So that's why it's 1.000. And so like you see, there is this number here, this thing here, this thing here. Which, yeah, it's 1. It was 1 to that decimal places, but and the matrix gives 1, but yeah. But yeah. Okay. Let me just flash the kind of things you have to do in the matrix integral. In the matrix integral, the sphere is basically the so-called free energy of the integral, which means, what does the free energy mean? Okay, I should write some equations for people who are not. So it's that first term we want to compute, that F naught. So Z is just integral D matrix e to the minus trace of some function of the matrix. So it's just that. And in large L, it's proportional to L square, and this F naught is the term that we are interested in. Now these matrix integrals that are dual to these 2 comma P models and also JT gravity also have a further epsilon in them. This epsilon is related to coefficients of V. So V is, let's say, typically a polynomial. It could be like h square plus 3 minus 2 epsilon times h to the 4th. I'm just making something up. It doesn't look like this, but point is epsilon shows up in these coefficients. And it shows up only with even powers. So coefficients of the potential have even powers of epsilon, and the thing you're supposed to do is to look for the first term, which is an odd power of epsilon. So this can be done fairly explicitly and for each P, and there's also even an analytic way to do it. But note that epsilon is going to 0, so we are keeping a smaller term compared to these guys. But these guys all are discarded because they're analytic in basically the cosmological constant. So the duality actually doesn't match the sphere to the sphere. It only matches the non-analytic piece in the cosmological constant. And yeah, you can say the same words about the disk. Yeah, you can compute, let me just flash some formulas for you to say that they're like very concrete. So for the disk, you find something like this. Like, again, you find some large pieces, but which are analytic in mu now and in mu b, and then you find these terms that you're after. But anyway, you can do this analytically for all p, and where is the answer? This is the answer, finally. So you see it's 1 times p times alpha to the p plus 2. It's the same thing. That 1 is, of course, this is exact in p for these values of alpha, but the Louisville thing that we computed was only for large p. So in principle, you could compute the 1 over p corrections by doing loops, 2 loops, 3 loops, and so on. And actually, these papers by Aninos and Moolman do some of that. Like they computed some higher order loop diagrams. But anyway, thanks for your attention.
Questions for Raghu?
Is there any Louisville, is there any geometry for the worldsheet in which the Louisville integral, the C factors can appear?
I think the C factors kind of always appear in some sense. I'm not sure why you insist on them not appearing.
Because it would be nice to like in the particle in the circle,
Yeah.
instead of computing a thermal partition function, you were computing a transition amplitude.
Mm-hmm.
The factor of C would appear. So what you can do is fix it by pasting together the two ends of the transition amplitude
Mm-hmm.
and comparing against the integral against the thermal integral, which had no C's, so that fixed the value of C. Right? So
I'm not sure, because when you have open things that you compute, there are further ambiguities related to how you normalize this state on the two ends.
right.
So you can't really fix C using that, because if you do integrals on manifolds that have boundaries, there are additional normalizations associated to how you normalize the boundary data on those things. So
But let's say that I normalize them physically, right? I mean, there is a result that is unambiguous, which is that it should be if I take its absolute value squared, that should be the probability that I measure in my lab.
yeah, and you will find all the correct results for those things, even if you keep the C around. I think the C drops out when you ask a physical question.
No,
It's not like it's
that's not
contaminated.
true. I mean, the partition function, the amplitude definitely has a C appearing when you're computing that transition amplitude. And that transition amplitude is definitely physical, right?
Well, the transition amplitude is just this, right? I mean, it's the square root of something like this, right? And you can just compute it, keeping the C's, and if you do it correctly, it should cancel. It should either cancel, or whatever the C that remains here will cancel, will give you a measure for dx. Because you have to set xf equals xi, and then integrate over x. So if you have any C's remaining in this formula, what that's telling you is telling you a measure for integrating over x at the end.
Sorry, I didn't get that last part. So if I had C's remaining on that formula,
Yeah.
you're saying
That to get the partition function, you have to set xf equals xi equals x and integrate over x.
appear on the measure.
Yeah, so that C, whatever that remains, will appear in this integration measure so as to the final answer for z of beta is independent of C.
Right, but do you agree that there an example of a physically relevant quantity that did have a C, which was before I did the integral over dx?
No, but that depends on what you mean by x, right?
Well, but the point is that before I integrated by x,
Yeah.
there was already the quantity was already physically relevant. There was an experiment that-
No. The C, if you do what you're saying, the normalization condition on wave functions would not be integral dx mod psi square equals 1. It would be integral dx over whatever constant mod psi square equals 1.
So why? Okay, so let
I
me
mean-
let me change it around. If I do keep the C before doing that integral, right? The value of C, and then I integrate over dx without the C, and I use this procedure to fix the value of C, I will obtain the correct answer.
Well, I think we should do the calculation and see. I can't say off my feet because I haven't done this calculation in this way. But I think there are multiple things here. There is the C which goes into the measure, but there's also just a normalization of the x. And those are two, again, different things. And I mean, I'm happy to discuss it with you more over email, but I'm pretty sure that that's what will happen. Yeah, any ambiguity that remains in this transition amplitude will have to be absorbed into the integration measure over x, or which is the same thing as what's the normalization condition for your wave function, like what's the measure, yeah.